Hey, it's Mr. Shrum, and I'm back again with a physical science tutorial walkthrough, and we're going to look at reflection and refraction of light. We talked a bit about that in a previous lesson, but we're going to look at uh, it a bit more in depth. All right, introduction. It's a rainy afternoon. You're looking at the sky through your window, waiting for the rain to stop so you can go out and enjoy the rest of your day. Suddenly, the sun starts shining through the clouds, and you see one of nature's colorful wonders, a rainbow, splashed across the sky. Rainbows are formed by reflection and refraction of sunlight from water droplets, which cause the white light of the sun to split into its constituent colors, the colors you see in a rainbow. It's not just a rainbow on a rainy day that can dazzle you with this spectrum of colors. You can see a rainbow, for example, when you look at a water fountain with the sun in the background, and you can see a spectrum of colors from a crystal chandelier or the beveled edge of a mirror or window. This color spectrum is also caused by the refraction of light. In this lesson, you will discover how light is split into the colors of the rainbow because of the refraction of light. You'll also explore reflection and see how devices such as solar ovens and periscopes apply this basic physical property of light. All right, let's go. Reflecting light. You have seen that when any incident wave hits a boundary of a medium, it is partially reflected back into the medium. Light follows this typical wave behavior and gets reflected when it hits the boundary of a medium. Most of the objects that we see around us do not emit light of their own, but they are visible to us because of the light that is reflected from their surface. Your reflection in a mirror or in a swimming pool is a common example of reflection of light. Recall that when a wave is reflected, there is no change in the speed of the reflected wave, and therefore no change in the wavelength. So the reflected light travels with the same speed and wavelength as the incident light. However, its amplitude may change. Ray model of light. Newton believed that light was actually a stream of tiny particles traveling at a high speed. Later experiments by other scientists revealed that the behavior of light is sometimes best explained by using a wave model, but in other cases, a particle model applies best. A simple geometric model called the ray model describes most everyday behaviors of light, whether it's acting like particles or like waves in its interaction with matter. According to the ray model, light travels as rays along a straight line. Light rays continue their straight line path until they encounter some barrier or boundary in the path. You can directly observe this straight line behavior of light in everyday events. When sunlight passes in a straight line through a small opening in a window or a door, its straight line path results in the pattern of light and shadows it casts. You can even see its linear path through the air in suspended dust particles. When light is incident on a shiny object like a smooth metal backing on a common mirror, more than 90% of the light is reflected back. This video shows the relationship between incident rays and reflected rays from a mirror-like surface. So let's see. Yeah, here's a bit of the video. Reflection and the angles of reflection and the angles of incident. In the video, light rays emerged from the dancer and hit the mirror at some angle with the normal. The normal is a line perpendicular to the surface of the mirror. These rays reflect off the mirror's surface at the exact same angle as the angle of the incident ray. The law of reflection states that the angle of incidence is equal to the angle of reflection. So whenever the camera is in the area where the rays are reflected, it captures the dancer's reflection. When the camera moves away from this area, however, it cannot capture the dancer's reflection. To find the angle of incidence and the angle of reflection, you can draw a normal to the surface at the point the light ray is incident. Figure 1 shows light rays incident on a surface at different angles, but in accordance with the law of reflection, the reflected ray also makes the same angle with the normal as the incident ray makes. In figure 2, you can see that when a light ray is incident at a 90-degree angle with the normal, there is no reflection as the incident ray continues to travel along the surface. When the angle of incidence is 0 degrees, as in figure 3, the reflected ray retraces the path of the incident ray. The law of reflection holds true for smooth and shiny surfaces as well as for rough and bumpy surfaces. But depending on the type of surface, the reflection is either specular, like a mirror, or diffused. This is a picture of specular reflection. First, let's look at specular reflection. So we have a beam of parallel light rays incident on a smooth surface. You can see that the light rays are also reflected off the surface in parallel. Such a parallel reflection of light rays is called specular reflection. It occurs when the light rays are incident on a smooth, shiny surface. A reflection in a mirror or in still water is a typical example of specular reflection. You can see a reflection perfectly in a mirror because light rays incident on it, on its smooth and shiny surface, are reflected back in parallel to each other. This is diffused reflection. And this is light beam incident on a rough surface. You can see that the light rays coming are parallel before they strike the rough surface. After they hit the surface, the rays are reflected at the same angle as the angle of incidence with the normal in accordance with the law of reflection. However, because the rough surface, the normals at the points where the incident rays hit the surface are not parallel. So the parallel incident light rays are reflected in all directions. This is called diffused. Because light rays striking a rough surface are reflected in all directions, we cannot see a complete reflection of the object as we can see with a shiny and smooth surface, such as a mirror. In addition to the everyday flat mirror, solar panels and periscopes are practical applications of specular light reflection. Both of these devices make use of multiple reflecting mirrors. A periscope is an instrument used to view objects that are above a person's line of sight. They are widely used on submarines to see what's happening above the water. A periscope is essentially a Z-shaped tubular structure with a mirror placed at a 45-degree angle at each of the two turns in the structure. The two mirrors are parallel to each other. And you can find out how periscopes work here. It lets you see over the top of things such as fences or walls that are too tall for you to look over. And you can also see around corners. Soldiers in the First World War used them to look out of the trenches without actually having to put their heads up out of the trench. And they're actually still used today in some tanks and submarines. A solar cooker or oven uses sunlight to heat or sterilize food. There are different designs for solar cookers, but most work on the principle of reflection. A solar oven uses multiple mirrors, or in some cases, a circular mirror to concentrate the sunlight falling on it. The energy from the concentrated sunlight heats the food. Find out more about solar cookers and ovens here. It takes us to the solar cooking wiki. But it's pretty cool if you want to check that out. And now we have a checkpoint question. A light ray from a source is instant on a mirror surface at an angle of 0 degrees with the normal. Which statement about the reflected ray is true? Well, the angle of incidence is 0, so the angle of reflection is also 0. This means the reflected ray will retrace the same path. All right, that was it for reflecting light. Next time, we'll look at refracting light. And until next time, stay safe, good luck, and I will see you guys next time.